In previous modules, we looked at signalling functionality. In this module, we're going to look at some of the factors that constrain where signals are positioned. We're going to look at their role in protecting junctions and other infrastructure, capacity influence on signal positions, braking distance considerations, signal sighting, and maintenance constructability and cost. Signals need to be placed on the approach to junctions as they serve as the entrance to routes over those junctions. They should be as close as the junction as needed so that it's not locked for an unnecessary period of time as trains travel from the signal to the junction, and also so they're not slowed down unnecessarily as a result of any approach control, but not so close that the signal's overlap locks the junction, because that would then mean that a train approaching the signal would lock up the junctions, whereas if the overlap is clear of the junction, the train can approach the signal whilst other train movements take place in front of it over the junction. The signals may also control passage and protect other infrastructure such as level crossings or swing bridges or tunnels. In most cases, only one train is permitted in each block section at once, which is protected by a signal. Hence, it's therefore necessary to position signals and hence block sections sufficiently regularly to support the required capacity. On low capacity lines, two-aspect signalling typically suffices, but where high capacity is needed, then typically 3 or even 4-aspect signalling is used that allows for much shorter block sections. But it's not necessarily on the plain line sections that capacity is constrained. It's often junctions and stations that prove the biggest capacity challenges, hence, going back a couple of slides, the importance of placing signals optimally at junctions and also at platforms, whereby usually the optimum position is to position a signal at the end of a platform so that trains going into the platforms aren't impeded when that signal is displaying a red aspect, and then whilst they're stood in the platform, the train in front can move ahead and that signal can clear to a less restrictive aspect. Signals also need to be placed such that there is sufficient distance for a train to stop between a first cautionary aspect and the corresponding stop aspect. In 3-aspect signalling, the first cautionary aspect is the yellow aspect, hence the stopping distance is from one signal to the next. And in 4-aspect signalling, it's spread over 2 signal block sections because the distance is from the first caution, the double yellow, to the stop aspect with a single yellow in between. The required stopping distance depends on the maximum permitted speed of the train on the line, the average gradients, the braking characteristics of the train itself. On lines with trains using different braking characteristics, you can either adopt the set stopping distance for the worst case performing train, or have differential speed restrictions whereby trains with better braking characteristics are authorised to travel at a higher maximum speed than trains with worse braking characteristics. But even so, the distance between successive signals typically exceeds even the longest stopping distance, which gives some flexibility in position and can reduce the costs by reducing the number of signals that are needed. However, the signals shouldn't be placed an excessive distance apart or irregularly, as this could lead to driver misjudgment when braking. Signals also need to be seen by drivers and for long enough that they are able to interpret their meaning. It typically requires about 8 seconds for a simple signal, maybe even up to 10 seconds for a more complex signal. And the faster trains are going, the longer the sighting distance that this time translates into, all of which can be interrupted by bridges over the railways, curves and other structures. On multi-track railways, there are further challenges owing to the ambiguity as to which signal applies to which lines. Hence, it's important to position them where this can be clear to the drivers. And similarly, where successive signals are close together, there is a risk of a driver reading the next but one signal rather than the signal that applies for the train that he or she is driving. And the similar sort of thing can happen in station platform, particularly curved platforms, where there's a risk of a train entering a platform, seeing a signal that is intended for a train already in that platform. Further consideration is a more practical one on maintenance cost and constructability. That signals should be easily accessible for construction and maintenance purposes, ideally close to access points with accessible walking routes to those access points, and also constructing new signals a distance away from existing signals so they don't obscure them during construction. Cost of constructing and maintaining signalling generally increases with the number of signals, so there's a good incentive to be economical with the number of signals that are needed to meet operational requirements, and also to mount them as cheaply as possible. Ideally, posts mountings are generally cheaper than gantries or cantilevers, and reuse of existing structures is generally cheaper than constructing new ones. So in summary, we've seen a number of factors that constrain where signals go and can influence the signalling scheme's design. Signals need to be placed to protect junctions and other infrastructure. They need to be placed sufficiently regularly to support required capacity. Distance between the first cautionary signal aspect to the corresponding stop aspect must be sufficient for a train to stop. And the signal drivers must be able to see their signals for sufficient time to interpret their meaning. And where possible, signals should be easily accessible for construction and maintenance purposes.